So as introduced, I'm Joyce NABENDE from the Department of Computer Science. Our background of myself and the entire team is computer science, software engineering, but we've been working very closely with the SIP team in Namulongue for this work, and we're going to present analysis and preliminary results that we have for using image analysis to predict sweet potato sensory attributes. Yeah, so I can go ahead and get started. So the outline of the presentation is we'll have an introduction, we'll discuss the process that we have gone through, and then we'll talk about the data collection and processing that we have undertaken, then the model development, where we'll also have results of the work and some aspect on model deployment and how we envision that the end users of these tools will be able to use the results of our work. As a way of introduction, I think from the RTP foods, we all know that color and appearance are different traits that are typically used by consumers as visual cues to make decisions about different quality attributes like taste, cooking quality, texture of a crop or a product. And looking at color and appearance, these are critical indicators for targeting the end user preferences for different crops in Africa, and like sweet potato or cassava, for example, that we are very all interested in. However, if we look at these sensory evaluation studies and the sensory evaluation panels, they tend to be very costly and very time consuming. And so there's a need for high throughput screening methods to identify indicators of these consumer preferred quality traits in different crops. And so based on that need, we came up with a way of using machine learning techniques in order to narrow this down and predict two sensory attributes for sweet potato, which is mealiness and color, which are very important for the breeding team in coming up with very good preferences or very good different crops for the particular end users. So the process that we undertook is first, for any machine learning task, we need data. So we first of all participated in the field data collection, where we have been able to capture data. There's a very good machine, the DIGIEye, that has been procured and is being used in Namulongue for image capture. So this has given us a very good data set that we have used, but our focus here was on the sensory data capture and also ensuring that the data can be securely stored in a central place that can be accessed by everyone. And so we've been able to get data that has been collected, as we'll see, from different sites in Uganda for sweet potato, and we've collected data for both the raw and the cooked sweet potato samples that we have used in our work. After the data collection, the next step has been the data pre-processing. We have the image data that we've collected. What is important is the feature extraction, extracting the features of interest from the image data. After collecting and extracting this, then we can feed this into the models, the machine learning models that we have developed for color and mealiness modeling and evaluation. And we'll discuss several models and give you some results from the models that we have been able to use. As I said, it's good that the tools that we develop can actually be used by end users. And so we've also looked at model deployment, deploying the models in interfaces, and in the process of also testing these end-to-end systems with the different end users of the tools. Yeah, so as a first step, we can see one of the colleagues in the lab is collecting and putting samples into the DIGIEye machine to be able to capture the image data that is automatically stored on a computer. But we of course go through our process of cleaning the tubers, cutting the tubers, getting the correct samples before they are actually put in the DIGIEye. And so we've had image data captured using the imaging system, and this helps us to get very good high resolution images in a controlled lighting box. This is critical because then we're able to have good data without any background that could affect the modeling that we do in the next step. We have so far collected over 3,600 images from 950 samples that have been provided to us by the team from Namulongue and SIP across different data collecting sites like Namulongue, Bulindi, Iganga, etc. These are different sites in Uganda. Also, on the other hand, we have been fortunate to also be given access to the human sensory data which has acted as our ground truth data that gives the scores that are given by the human sensory evaluation panel, especially also on the milliness by hand, but also for the orange color intensity. There's a scale that they use. And so we've been able to get these results where they're scoring different samples. And we have used this as a way of validating the different models that we have developed. And so we've collected and obtained data, on ground truth scores for 227 samples, 120 from the 2021 harvest and 107 from a recent harvest in 2022. And these have been scored by human experts across different sensory attributes like milliness by hand or orange color intensity, but it's a whole list of different other attributes that you can see, and we've only provided a sample here on this slide. So after collecting the image data from DIGIEye, and the first step was, so we collected data to say for both the raw samples and also the cooked samples as well, because we have been using the raw samples for the color intensity our calculations and modeling, whereas we have been using the cooked samples for the milliness that we've been calculating and modeling. And so as a first step is that we have been able to, from how many? Yeah, so the first step has been the background elimination, where we want to only retain the objects of interest. So as you can see, when the different samples are taken, they're attached to a label because these different samples belong to different varieties that have been grown. And so it's important that these are attached to the labels that we have. But when we're doing our modeling to be able to feed this into the machine learning models, we only want to take the actual images. So we do background extraction, where we eliminate all the different background and only stay with the different samples that we have. And so we've used several techniques like image segmentation and color clustering as well. And then we've also been able to extract the pixel intensity values for the RGB channels from the images that were taken by DIGIEye, and then the pixel values are extracted using both the DIGIEye machine, and we have also automated Python scripts that we have implemented that help to extract these RGB values, and the DIGIEye values are used to validate the values obtained from the Python script. So the pixel values that we have obtained in the RGB color spaces lie between 0 and 255. And we have the samples that we take, several samples. We have several states of the samples. For example, we can have the raw after the peel. We can have the cooked cross-section, as I mentioned earlier, or the raw cross-section as well. And we've been able to obtain the values for each of these, both using DIGIEye, but also using the Python, which is good because then it helps us to see that the models that we've developed are actually also synchronized with the values that come out of the DIGIEye machine. And then for milliness extraction, we also used automated feature extraction from the images. First of all, the images were converted from a TFI to PNG format just to try and reduce the sizes of the images as we try and feed these into the models. And so in terms of modeling, we have used already existing pre-trained CNNs, convolutional neural networks, to process and extract the features from the images. And we've used several architectures of the CNNs like the efficient net V5 and VGG16. And these extracted features are then stored in a format that can help us to improve access for the different kinds of modelings, because we want to understand which different aspects are affecting or contribute to milliness of the samples or the image samples that we have. Then in terms of color intensity experiments and results, I will let my colleague take over and go into details. So Jeremy, please feel free to come in and talk about this.
Thank you, Dr. Joyce. I hope you can hear me. Should I use your screen?
Yes, you can use my screen. Please go ahead.
Okay, all right. Thank you. Yeah, so in terms of the experiments for the color intensity regression experiments, we are trying to predict the mean orange color intensity value that is shown in the ground truth data that we get from the human sensory panel. And for this, we run with a total of 6 models. We have only shown the best performing models here, which was a linear regressor and the lasso regressor. And these attained an R-squared score of 0.91 and 0.90 respectively. And those are the values for the mean absolute error. And considering the R-squared value, of course, the linear regression model here slightly edges out the lasso regressor. And then for the classification experiments, these were also run with about four models. We haven't focused a lot on this because the better results are coming out for the regression experiments. But here are the best results that we achieved for the random forest classifier shown over there in terms of precision, recall, and the F1 score. So just slightly a bit above average, although we have pretty good performance for the regression experiments. The next slide, please. All right, and then we also do some post training evaluation, and these are some samples selected from the test set. And here, what we want to see is, okay, what was the ground truth value, the predictions, the error, or the difference between the two values, and then refer this back to the original values from the human sensory panel. So in the ground truth data, we do not only receive the mean values, but we also get the original data that was used to come up with the mean values. And from this, we are able to establish the range within which the experts on the sensory panel assigned a color intensity value. So from here, we're able to tell, okay, even just beyond the error, are we still falling within the range of what the experts were predicting? And we can see from just this randomly selected samples from the test set that for most of them, we're actually falling within the range, although there are a few samples where that may not be the case. But in this case, for this post evaluation, we see that the milliness predicted milliness value falls within the original range that all the experts gave. The next slide, please. And then for the milliness experiments, and this was for the regression, we ran with 4 models with our data set, which had images for 91 samples. And of course, we did 80-20 split. That's for the training and testing set respectively. But we also use cross-validation in the training to ensure that we have as much variation as possible in the model. The next slide. Yeah, and so this is a summary of the results that we had for the regression experiment. So like showed earlier, we have 2 targets. We're targeting milliness by hand, so that's a mean milliness by hand, and then also the positive force 1 R value. And from this, we can see that we have the best performance coming in from the random regressor, although the XGBoost model and the neural network are really close if you consider the R-squared values for this. The next slide. Yes, and then we also do some post analysis here. We just sampled some of the top 3 and then the worst 3 samples from our test set to try and show what the variation is, and we can see that that for most of the samples, the predictions are really close to the milliness by hand, but actually the sample now, for instance, the sample we see down there, we can already get insights and see that the error is really large, but this can also be related back to the fact that we had a few samples whose in the ground truth data whose milliness was low, as many of the values had a high milliness value as scored by the human sensory panel. And these are kind of the insights we get from this from this analysis, and we can use this information to optimize our results further. The next slide, please. Yes, so we've also gone ahead to think about how do we deploy this. And for now, we've developed a prototype tool, which is a web interface through which you can interact with these models. So the interface allows you to upload some images and get back results, the result being either the orange color intensity predicted by the model or the milliness predicted by the model. And this tool supports batch image processing so that we have we can process a lot of images to increase the throughput. And the next slide. And this is just a picture illustrating sort of like what you would see in this tool. So it's currently a prototype, but you can upload images and then just click a button to post to send the images, and the model will run these images and then give back results. These results, of course, we shall be able to present in a CSV or an Excel file for further analysis. And we also think having web tools is a good basis to start building on tools that can be used by many others. Yeah.
Yeah, thanks, Jerry. Of course, the plan is to eventually have these tools within BreedBase that everyone else within the the sweet potato community or RTB food, can be able to have access to them. Yeah, thanks. I think that's the end of our presentation.
Thank you, Joyce. Thank you, Jeremy, for this very clear step-by-step presentation containing lots of really interesting results, which are of high interest for our RTB food scientific community. And I confirm that this work you've just presented is very much aligned with our RTB Foods priorities, because we are aiming at developing high throughput tools to help breeders better integrate consumers' preferences as breeding priorities in their breeding pipelines. So thank you very much. I think we had a question in the chat box from Brigitte, but it has been answered already. So colleagues, if you have questions or comments for the Makerere team, please feel free to raise your hand or write it down in the chat box directly. Yes, Fabrice. Okay, you applaud.
But it's not a razor in my hand. This.
No, it's applause.
Where is your hand? Oh, sorry. It's okay now.
Yes, please, Fabrice.
Oh, sorry. So just to say that I would like to say to Joyce, thank you, because I've been in, she was not here this morning, but Anne and Francis and Judith give me the opportunity to visit the lab and to see the teams. Very, very, very impressive team, young and so efficient. So impressive. So it's very, as you say, Eglantine, it's very important for us, for RTB Food, what they are doing using DIGIEye. One of the observations I done this morning, it was regarding the color quantification using the answer from sensorial panel. I was surprised because, so maybe Francis knows that because they will work on this. I asked why they don't use directly the data coming from the DIGIEye, because the DIGIEye is able to deliver the data in trichromatic coordinate. So it could be LAB or it could be red, blue, green. So why we don't try to use directly the data and to see if these data are related and correlated to what consumer. Maybe Mariam can tell a word about this. Is there a relation between what we get from LAB from DIGIEye and the consumer perception of the orange color?
Yeah, thanks, Fabrice, for the question. So the question is about if there's correlation between what we get from the DIGIEye and what that sensory panel is giving us.
Yes, especially in terms of color, yes. Because
yeah,
you know, you get from the DIGIEye, you get the color space. So it's a syllab or not, but you can transfer in another color space if you want, but it's syllab and so LAB, for example. So did you try to see if there is a correlation between the lab and the coordinate you get from the DIGIEye?
Okay, so Claire, please answer the question. You've been working on the color work, correlation, of course, between DIGIEye and the sensory panel, as well as the model. Yes.
Yes. So we, as we explained, Fabrice, this morning, so what we did for color much earlier, first to do with the data exploration, we tried to establish the features that can help us to model to model the color problem. And from this, what we did was to look at the pixel intensity values. So we did notice, just like we visualized on the histograms, that there is a difference, especially on the red and green channel for white fleshed samples, orange fleshed samples. And so we decided to use the RGB values to model for color. So initially what we did was to extract these RGB values using the automated script. But for us to be able to validate whether the values that we obtained are correct, we went ahead and extracted values from DIGIEye, from the DIGIEye machine. So we did extract RGB values. This was not done on all samples because it's manual work. You have to look at it on a sample basis. But we did this for a couple of samples over the different color intensities. And on comparing what we got from DIGIEye and what we got from the automated script, we noticed that the values, the RGB values, were in the same range. So you'd find that there is a difference either of 0 or of 1, -1, +1. Yes, and so with that, we decided to go ahead and extract the RGB values for the other samples using the automated script, given the fact that the pipeline was automated. But that was done after we had established that there is a correlation between the values that we got from our script and the values that we got from DIGIEye. And then the values that we got from the sensory panel, we use these values as our target value or as our label, what we would intend to predict at the end of the day. Thank you. I hope I've answered the question.
Yes. Yes, thank you.
Thank you, Claire. Thanks, Fabrice, for your comments and your feedback on the discussion you had this morning with the team. Is there any other question from the audience? Or maybe a comment from Mariam from SIP, who has been involved in the laboratory and sensory characterization or activities. Okay, Michael, please go ahead.
Right, thank you, Eglantine. And that was a very good presentation. I just wanted to ask, as a follow-up to the remarks from Fabrice, I really don't get if we have been able to check if there is a clear correlation between the DIGIEye values and LAB. I really didn't get that so clearly. Did we check if the RGB value from DIGIEye corresponds with the LAB from the color space? Then secondly, I would like to know what is the spectral range, what is the wavelength range for the DIGIEye imaging system? Then lastly, the web tool for model deployment. Is it a tool available for the public to use? What stage of development is it? And do you provide it for other users to upload image and be able to predict the image values? Thank you.
All right, thanks, Michael, for those questions. I'll answer the second part, and then a colleague who has worked closely with the DIGIEye will come and answer the first part of the question. So for the model, we are almost complete. We only presented this to the team in Namulongue, I think 2 weeks ago, for their feedback. We have received feedback from them, and so we are incorporating that and finalizing the tool. We want to ensure that the tool is open to the public, and that's why I mentioned that it's going to be a web-based tool. We can always provide the URL where people can go back and upload their images, but of course the eventual plan is to try and make sure it's in read-based where anyone can have access to it. So I will request Anne to talk about the DIGIEye question.
Thank you, Dr. Joyce. Can you hear me?
Yes, Anne, go ahead.
Okay. So when it comes to the color spaces that the DIGIEye provides, it has the lab color space and the RGB. It has other options as well for the color space, but we focused on the RGB because it approximates a bit to human vision. We can get all the pixel intensity information that we can get from an image using RGB, and also the DIGIEye being able to give us RGB values. We took that because we could approximate that as well with automated process. We also extracted lab values from the DIGIEye and we converted them from lab to RGB to check the similarities, and it is it's a very high similarity. So that's why we chose RGB, because it is quite a common lab color space, plus it gave us accurate results. I hope I answered your question.
Thank you.
I don't have really much to say. I was hoping that Dr. Sally would be here, so I wouldn't have to say anything. But thanks, Joyce and the Dr. Nabende and the team. And then maybe just one thing in addition to what Fabrice asked. Maybe it's something that I picked that was a little bit off. Maybe I picked something wrong, but he asked about whether the results that we get from the DIGIEye, the readings that we get from the DIGIEye, because it's a machine, are they related ultimately to what we would expect the consumer, not just the sensory panel, the trained sensory panel,
Yes.
the consumer
Yes.
to update? And I think that unfortunately the team from Makerere is probably unable to answer that. So I'll try and answer it. We have not yet directly compared results from the DIGIEye machine to results from consumers. Currently, what we are doing is we're moving away from trying to use consumers to describe products, and we are using just the sensory panel and descriptive sensory analysis to do that. But we hope that in the future, we'll be able to just, at the very least, compare the differences in the results we get from the DIGIEye and how consumers appreciate the color or appreciate some visual aspects, appearance characteristics of the product. And then we can make correlations in that sense, but not really in the sense of the color that, that consumers see or describe, comparing that to the LAB values or the RGB values from the DIGIEye. I think we will be using for that. For description, we will be using, for human description of color and appearance characteristics, we are mostly using the descriptive sensory analysis for now.
Yes, thank you.
Thanks, Mariam, for this interesting comment. Indeed, now one of the next steps, but it's not only, applying to this specific product and this specific tool, but for all methods developed in RTB Foods, one of the main remaining objective is to define the threshold of acceptability from consumers. I mean, define the lower threshold and the upper threshold for all key priority quality traits for the different food products we have been working on. So it's one of the main remaining steps. And of course, breeders need targets. So we need to define these targets, carrying out laboratory analysis using the different methods we have been developing together in parallel to consumer testing. So this is really important. Thanks, Mariam. There's a question in the chat box from Simon. Simon is asking, so thanks for this great work. So to use the web app, images must be generated from only DIGIEye. So this is a question.
So the web app is just an interface to upload the data and interact with the models. So technically speaking, you could upload in any anything there. Maybe the question is pointing to whether the models would work with any images aside from images from DIGIEye. And for now, the models have entirely been trained on images captured using the DIGIEye system. So it's still difficult to tell if these images were captured in a different setting or using something different, if this would be repeatable. So we cannot, it's difficult to guarantee what the model performance would be like for images captured that are not captured using the DIGIEye system, but it's definitely worth something to investigate. I think also Fabrice in the morning was talking about the format of the images. And so far we've been able to build the models, not just using the original images from DIGIEye, which are really high resolution, but also with a scaled down version of the images, and which is important, of course, to improve performance for experiments, but also it would be, I imagine, easier to upload 50 MBs of images rather than, let's say, upload 5 gigabytes of images. So we've tried with 2 different versions for the model development, and the results are reproducible, or they are very similar. And at least we know that that works. That's as far as we've tested, but I think it's definitely worth trying out images from other settings if there are such images. Thank you.
I just have a comment that we had this morning in the discussion as well. Is the next challenge will be to try to do, because mealiness for the moment is correlated with cooked images, so cooked sample images. The next challenge will be to try to do a relation between raw sample images and mealiness. So we had this discussion this morning, and I know that the team is starting to work on it. But for RTB food, it's one of the main challenges to do phenotyping. So we need to be able to avoid cooking step.
True. Yes. The objective is to create high throughput tools. So cancel the cooking step, of course. So develop models on raw products, raw crops, indeed. Any more comments or questions for the team? Dr. Joyce, do you want to say a last word before we close this webinar?
Yeah, first of all, thanks a lot, Fabrice, for making time to come to the lab. I know I wasn't able to meet you, but thank you so much for visiting and for all the interest and feedback on the work, and we'll take that as we try to keep improving the models. And thanks everyone who has been able to attend this RTB webinar. It's the first one for us, and we're very grateful for the feedback that we have received. And thanks, Eglantine, for organizing this and keeping up with me and with the team to make sure we can present today. So thanks, everyone.
Thank you. You're very much welcome. Thanks, and thanks to your team, indeed, Jeremy and Claire. It's an impressive team. Thank you for your presentation and for these very interesting results. So we are looking forward to the next steps. So thanks for this webinar. Thanks for joining, everybody. So let me just inform you that in 2 weeks' time, we have a webinar which will be managed by Amos Asimwe, who is the RTB Foods Data Manager based at CIRAD Montpellier. And Amos will demonstrate the whole process one has to go through to upload sensory data onto BreedBase, to make this sensory data acquired on breeding populations or on whatever breeding material available to breeders for selection purposes. So Amos will show us step by step how to upload sensory data coming from sensory panels on BreedBase, which is one of our main commitment in RTB Food, is to make this data available for breeders for selection purposes. So we see each other in 2 weeks' time. And take care meanwhile, and have a nice weekend. Goodbye, everybody. Thank you.